In this video, we're going to review the Chapter 4 test that's in the Blitzer textbook. First problem, graph these two exponential functions. First, let's talk about the intuition of the first function, which also the majority of which will apply to the second one. We have y, or f of x, equals 2 to the x. Is this a legal exponential function? The answer is yes, and the reason is that the x is in the exponent. It's not down here with the coefficient, or I should say it's not down here with the base. Also, this base is a legal base. Let me just get the other one down. Okay. In order for a function to be exponential, the base has to meet certain criteria. And it's best to just look at this number line, in my opinion. 0 and 1 are going to have open circles. And anywhere that I now shade in is legal. So I'll use green for legal, and anything in red is illegal. Okay, so theoretically I could also make this red, because it cannot be 1, it cannot be 0, and it cannot be negative. Just to be specific about this, if this base was negative 2 to the x, that would be a legal exponential equation, exponential function, because that negative really refers to a negative 1 times 2 to the x. And because of PEMDAS, we would do this exponent first and multiplication second. What is not a legal function would be this. That would be an illegal function. Okay, so again, legal are things like fractions, because that's between 0 and 1, or whole numbers like you see in this problem. Okay, let's talk about how to graph these and what the intuition is with respect to f of x. Because the base is positive, and because it is a whole number, it's not a fraction, I know this is going to be a growth problem. Growth problems move away from the horizontal asymptote. So we're going to get something like this for this graph. The horizontal asymptote here is going to be y equals 0. And the reason that's the case is because these functions have the generic formula where the k represents the horizontal asymptote. So here the k is 0, so our horizontal asymptote is going to be right here. As you move from left to right, this graph is going to move away from the horizontal asymptote. Now as we look at g of x, everything that we just said is true, and in addition we see that this g of x is going to be shifted in the horizontal direction. You see this negative in the generic equation. Whenever you have a negative in a generic equation, then what you see in the real world, it's opposite to what really happens. So in other words, if I circle that positive 1, because of that minus sign, I'm going to take the opposite. So we are going to see a shift in the negative direction of 1 unit of this graph f of x. That's the intuition for this particular problem. Okay, now let's do what they say. They want us to graph it on the same coordinate plane. The way you graph exponential functions is as follows. You take this construct and you set that equal to 0, and you set it equal to 1, and whatever x values are revealed, that is what you use in your table. So let me do that a little bit differently. The construct for f of x is x plus 0. So I set that to 0 and to 1. So we get x equals 0 and x equals 1. Here, we're going to set this equal to 0, and the construct also equal to 1. This is going to give us x equals -1. This is going to give us x equals 0. So these are the x values we are going to use in our table for the respective graphs. Okay, let's do f of x here. And let's do g of x here. Okay, so we're going to plug in 0 and -1 here. And on this side, we're going to plug in 0 and +1. I'm sorry, I did that incorrect. Yes, we're going to do x equals 1, +1 in green, and -1 in red for the reasons that we just talked about. Okay, now, if I plug in x equals 0 to f of x, I'm going to get 2 to the 0, which is 1. And if I plug in 1, I'm going to get 2 to the first power, which is 2. And over here, with g of x, if I plug in x equals 0, I'm going to get 2 to the first power, which is 2. And if I plug in -1, I'm going to get 2 to the 0 power, which is 1. So these are the points I'm going to graph. Let me make some room. I apologize for taking time to do this. Okay, so here is our coordinate plane. They want us to do it on the same coordinate plane. So let's graph f of x first in blue. The horizontal asymptote is going to be the same for both of them. Okay, so that's going to be right here. That's our HA, and that's the line y equals 0. They're both growth functions, so as we move left to right, we know that the graph is going to move away from the horizontal asymptote. So let's do it in blue first. We're going to plot the point 0, 1, and 1, 2. Okay. And our graph is going to do something like this for f of x. Like that. Okay, this is the point 0, 1. This is the point 1, 2. Okay, let's do g of x now in red. We're going to have the point 0, 2 and -1, 1, like that. And our graph is going to do this. This is g of x, and this is f of x here. So look what happened, ladies and gentlemen. This is the point 0, 2. This is the point -1, 1. So look what happened. Just as we predicted, there was a shift in the negative direction, 1 unit, in the horizontal direction. So this x value went from 0 to -1. This value went from 1 to 0. And in both cases, the y values stayed the same. That is the graph of the exponential function. Let's go to the next problem. 2. We're going to skip that. Okay. Write this in exponential form. Log base 5 of 125 equals 3. Here, we're just going to do Whirlybird. 5 to the 3rd power equals 125. Okay, now, the next problem is number 3. They want to write this, want us to write that in logarithmic form. So we have the principal root of 36 equals 6. Whenever you see roots, square roots, radicals during this chapter, during this section, immediately switch it to the fractional exponent. It'll make your life so much easier. Okay, so this is an exponential form. By definition, there's an exponent. And they want us to write this in logarithmic form. Well, logarithmic form has to involve the word log. So that's the first thing I do. The second thing I do is I ask myself, what is the base in the exponential form? And the answer is 36. I make that the base of my log. So base of the exponent becomes the base of my log. Then I envision doing whirlybird. So I envision what happens if I'm going to do whirlybird. Well, I end up with 36 to the 1/2 power. That means on the other side of the equal sign, I have to have 1/2. All right, so I have 36 accounted for as the base. We know that if we do whirlybird, 36 is going to be raised to the 1/2 power. The only thing left is 6. So 6 becomes the argument. And that's how you do it. So this in exponential form, you write down the word log. You look at the base of the exponent form. You make that the base of the log. You envision whirlybird. In whirlybird, you're going to raise 36 to something. That something is 1/2. That comes here. Only thing that is left is 6. That becomes the argument. Next problem. Okay, find the domain of f of x equals natural log of 3 minus x. So ladies and gentlemen, this cannot be negative. So what you do is you just set that argument greater than 0. And when you do that, you get 3 minus x is greater than 0, 3 is greater than x, or another way to say that is x has to be less than 3. So the domain is going to be negative infinity to 3, and we're going to use a curved bracket here because there is no equal sign in that inequality. This is your domain. Next one. Okay, so in problem 6 and 7, they want us to expand the functions that are shown. So let's look at the first one. Log base 4, 64, x to the 5th. Whenever you see multiplication in a log, you can expand that using addition. So this becomes log to the base 4 of 64 plus log to the base 4 of x to the 5th. Now folks, we can evaluate the first term with a little miniature problem here because we could do whirlybird. So what we're going to do is we're going to see if this can be evaluated. We set that equal to x. We do the whirlybird move. 4 to the x equals 64. We know that 64 is 4 to the 3rd power. Therefore, x equals 3. So I'm going to replace this log to the base 4 of 64 with 3. For this next one, I'm going to take advantage of the property that says we can bring that exponent in front of the log, like so. This is your final answer in simplified form. Next one. They want us to expand number 7. Okay, now the first thing I think of when I see that radical is I'm going to take that radical away and replace it with a fractional exponent. We are allowed in this scenario to expand this, recognizing that the argument in the denominator is going to have a -1 coefficient out front. So this becomes log to the base 3 of x to the third. That has a positive in front of it because it's in the numerator, minus log base 3 of 81. Just like in the previous example, we could do a little miniature problem here and evaluate this. Okay, when I see 3's and I see 81, when I see 81, I think about 9 times 9. When I see 3's, I think about 3 times 3. That immediately triggers in my mind that I can evaluate that. So if we have log base 3 of 81 equals x, we do whirlybird, and 3 to the x equals 81. Sorry, getting off the board here. 3 to the x equals 81. 3 to the x equals 9 times 9. 3 to the x equals 3 squared times 3 squared. When we have a common base and we're multiplying, we're allowed to add the exponents. So we have 3 to the 4th power equals 3 to the x. Therefore, x has to equal 4 because the exponents match. Okay. Let's clean this up a little bit. And replace this with 4. So now we have log base 3 x to the third minus 4, and then we can bring that out front. Final simplified answer is going to be log base 3 of x minus 4. Number 8. Here they want to write each expression as a single logarithm. So this is called condensing. So notice we have 2 logs here. We're going to condense that into 1 log. So we're only allowed to write the word log once. Immediately I see that both of these have positive in front of them. That means both arguments are going to be in the numerator. I'm going to go ahead and take this coefficient out front and move it to the exponent position. Because this is plus, I'm going to put x to the 6th in the numerator. Same thing over here, I'm going to move that, become y squared. These two expressions are equivalent. Remember, with logarithms, as long as the base is the same, and as long as there is no coefficient out front, you can combine these logs and make them into multiplication, 1 log instead of 2. But you have to go ahead and move that 6 and that 2 out of the coefficient position and into the exponent position in order to do that. So what you see here is our final answer. Next one. Okay, on this one, there's a negative here. That means this argument is going to end up in the denominator. We can't do anything yet because there's a coefficient in front of this logarithm. We have to move that 3 first and then condense. So we're going to write natural log once because we're condensing. We know there's going to be a fraction because of this negative sign. Here there's a positive sign, which means that argument goes in the numerator. And we're going to bring this up here and put x to the 3rd power in the denominator. And that is our final answer for number 9. Okay, next one. Log base 15 with an argument of 71, and they want us to evaluate this. This problem, as is not calculator friendly. You cannot go to your calculator and enter anything with a log to the base 15. The only thing you can do is see a log button, which has a base 10, and an ln button, which has a base e. So how do we change this into a calculator friendly form? Well, we use the change of base formula. The change of base formula allows us to make this calculator friendly. This becomes ln of 71, actually, log of 71 over log of 15. This base can be anything we want as long as it's the same base. We could leave it as log, which would mean that the base is understood to be 10. We can enter that in a calculator. You'll get some number divided by some number, and you'll evaluate it. In fact, if we do that, you end up with 1.5741. Or we could make that log anything we want. We could use base 4. We're not going to do it here because this problem wants us to evaluate this. But you might want to do that with a different problem where you have something like this. There's another term with the log to the base 4, and you're looking to combine something. You could pick 4 there and use that to combine these terms. But for this particular problem, they only want us to evaluate. So our two choices are to do what we just did, or we can do this. What you see in yellow is the same thing as log to the base e, and it has that special name of the natural log. You can enter this into a calculator and you'll get that same answer. Change of base formula. Calculator unfriendly, log of the argument goes in the numerator, log of the base goes in the denominator. You choose your base, whatever you want. If you're just evaluating, pick something calculator friendly, either base E or base 10, base E or base 10, and use your calculator. Next one. Where are we? Okay, we're down here. Okay, number 11. We have 3 to the x minus 2 equals 9 to the x plus 4. Whenever I see 3's and 9's, I know that 3 is going to be the star of this movie. I know that somewhere along the line, we're going to be converting 9 into 3 squared. So let's do that right off the bat. Now, let's use the power rule. The power rule states that we could multiply the exponents in this situation. You have a power raised to a power, we multiply. When we do that, this becomes 3 to the 2x plus 8. So now, folks, we have three to the x minus 2 equals 3 to the 2x plus 8. We have an equal sign here. That means these two entities are equal. We have bases the same. So if these are equal to one another and they have the same base, this has to be true that these exponents are equal to each other. And then when you solve for x, you end up getting x equals negative 10. I trust anyone watching this video is able to solve for x easily. Okay, now we have 5 to the x equals 1.4, and we're asked to solve this. This is number 12. Okay, so how do we approach this? There's no way to get a common base here like we did before. You don't see 3 and 9 here, or 2 and 8. So the only way to solve this is to use logarithms. Now you could either use log or natural log. The key is to use something that is calculator friendly. So let's use log of 5 to the x equals log of 1.4. We're now going to take advantage and bring that x in front. So we're going to get x times log to the 5th equals log to the 1.4. We're going to divide both sides by log of 5, and you're going to get log of 1.4 over log of 5. And when you punch that in the calculator, you get 0.2091. $13. 400 e to the 0.005x equals 1600. First thing I'm going to do here is I'm going to divide by 400 both sides. I'm going to cross off these two zeros. This becomes 4. So I'm going to rewrite this as e 0.005x equals 4. Okay, now, can't get a common base between e and 4. E is 2.71. The only way to solve this problem is to take logarithms. Now, we have a choice. We could use regular log, or we could use the ln function. I'm going to choose to use the ln function. Why? Because of that e. So let's do that. What is the base here? It's e. Whenever you have a logarithm with a base that matches the base of the argument exactly, you cross these out. So this simplifies to that. All you have left is the exponent. Divide both sides by 0.05. 0.005. And when you punch that into calculator, you get x equals 277.26. You should try to punch a few of these examples in the calculator just to get used to doing the calculator correctly. In the calculator, you're going to use e to the x. You're going to use the xy button to raise things to an exponent. Of course, you're going to use the log and the ln button. Make sure you try a few of these examples on your own to make sure that you get the same answer that I do here on the video. Okay, next one is 14. Okay, 14 is very interesting and not immediately straightforward. E to the 2x minus 6 e to the x plus 5 equals 0. Whenever you have an equation where this exponent is twice this one, that is a hidden quadratic equation. Okay, indeed, this times 2 gives you 2x. That is the same thing as having x squared minus 6x plus 5. There's a hidden one here. This is twice that. So we're going to treat this equation up above as a quadratic equation. Okay. What we're going to do is we're going to change this to e to the x squared, because indeed, if you use the power rule and you multiply these, you get 2x. We're going to change this to 6 times e to the x plus 5 equals 0. Now at this point, I think it's easier if, rather than working with e to the x, we let e to the x equal u. So this becomes u squared minus 6u plus 5. We factor this, and we get u minus 5, u minus 1 equals 0. U equals 5 or u equals 1. Now our goal here is to solve for x. So now we're going to bring e to the x back into the loop. So if e to the x equals u, then what we have is e to the x equals 5 and e to the x equals 1. Okay, we can evaluate these. And the way you do it is you take the natural log of both sides. Again, we're trying to solve for x. There's no way to get a common base between the 5 and the e. And we take the log of both sides, and specifically we're going to use natural log of 5 and natural log of e to the x. When we do that, we remember that when we have a base in the log matching the base in the argument, these cancel out, and we get x equals ln of 5. That is one solution. The next one is we're going to now evaluate this one. E to the x equals 1. We're going to do the same thing. We're going to take the natural log of both sides. The natural log of e to the x equals the natural log of 1. There's a hidden base e here. Whenever the base of the logarithm matches the base of the argument, they cancel out and you are left with the exponent. So x equals the ln of 1. Now we could simplify ln of 1. How do we do that? Well, if ln of 1 equals x, then we know that there's a base e there, and if we do whirlybird, we know that e to the x equals 1, therefore x has to equal 0. So for those of you that haven't memorized that ln of 1 equals 0, that's how you derive it. So here are our two final answers. So to review, when you see something crazy like this, look at these exponents. If this is twice that, it's a hidden quadratic equation. Note, remember that 2 times x is the same thing as x times 2. So all we have here is e to the x raised to the second power. These are the same. Once you have that, you just set that equal to u, and then we factored it and set both of these equal to 0, solve for u, replace the e to the x back in there, solve for x using logarithms. So a very interesting problem. Next is number 15. Okay. Looks to me, as I'm writing this down, that we're going to use whirlybird and solve for x. That's my intuition as I write this down. So I immediately say to myself, did I miss 14? No. I immediately say to myself, I'm going to do whirlybird. So I'm going to set 4x minus 1 equals 4 to the third power. I'm sorry, I wrote that down wrong, didn't I? That's a 6. Okay, apologize. Six to the third. 6 to the third power equals 216. So we have 4x minus 1 equals 216. And when you solve for x, you get x equals 54.25. Okay, that was number 15. Let's go to 16. Okay, we have 2 times the natural log of 3x equals 8. Okay, there's 2 ways to do this problem. The first way is to take this 2 and put it up here and rewrite this as the natural log of 3x squared equals 8. Now you have to be careful. When you square 3x, you have to make sure you apply that exponent to both the 3 and the x, both factors. So that's going to become 3 squared x squared equals 9x squared. Okay, so that's one way to do the problem. But quite frankly, I think it's easier if right from the beginning you just divide 8 by 2. So we do not do this maneuver. Rather, we just divide both sides of the equation by 2. So now we have natural log of 3x equals 4. We know there's a base e. We do Whirlybird. And get e to the 4th power equals x. 3x, I'm sorry. We divide both sides by 3, and our final answer is going to be x equals e to the 4th divided by 3. And I don't know if your teacher will accept that. If not, you just put 4 and then e to the x button divided by 3 and just put down whatever that computes to. Okay, we are now on number 17. All right. So what's going on here? We have the same base, log to the base 10. We have addition. Therefore, we can condense this and make a multiplication problem. When we condense, we're going to go from log written down twice to log written down once. Oops. There's no minus sign in front of here. There's no minus sign here. Therefore, these are going to become factors both in the numerator. Now we have to solve this. So the way to solve this, folks, is to remember that there's a base 10 here, and then we do Whirlybird. So we know that we're going to have 10 squared equals x times x plus 15. That's going to distribute to x squared plus 15x. I'm going to bring the 100 on the other side, equals 0. We are now going to factor this as x plus 20, x minus 5 equals 0. Therefore, x is going to equal negative 20, or x is going to equal positive 5. This gets rejected because if we plug in x equals negative 20 there, we're going to get a negative argument. Can't use it. Therefore, x equals 5 is our final answer. Okay, number 18. Similar problem, but as I look at this, first thing I notice is the bases are the same. There's no coefficient out front that we would have to move to the exponent position, so we can condense these logs. When we do, because of that minus sign, that argument goes in the denominator. So let's do that. So we're going to condense the left side of that equation. We're only going to write natural log once. We know there's going to be a fraction. X minus 4 is going to go in the numerator because there's a positive sign out front. X plus 1 goes in the denominator, and we're going to set that equal to natural log of 6. Both of these have the base e. So if you have the natural log of this argument, the natural log of that argument equals the natural log of this argument, then you know that the two arguments must be equal. The other way you could think about this is you could raise both of these to the exponent e. That's called exponentiation. And that allows us to cancel these two. Whenever you have an exponent with a base e and you have natural log to the base e, those can be canceled. It's very similar to having this situation. Whenever you have the base of the log equal the base of the argument, they cancel and you're left with the exponent. Up here it's very similar. Here, the base of the exponent, here in red, matches the base of the logarithm. Same thing, you cancel those out. So now we have this equal to this. I'm sorry, that was wrong. We have that red circle equal to 6. So let's do that. Okay. So we're going to set the two arguments equal to each other. We're going to put a hidden 1 there, and we're going to cross multiply. Whenever you have two fractions facing each other with an equal sign in between, it's an invitation to cross multiply. So we're going to end up with 6x plus 6 equals x minus 4. And when you solve for x, you're going to get x equals 2. But hold on, we are not done. You have to check your answer. And when we do, what do we notice? If we plug in x equals 2, right there, this whole argument becomes negative. Therefore, this is rejected, and the final answer is no solutions. It's a great problem. Okay, let's go to D now, as in delta. Okay, so what's going on here? Here we have this complicated equation. They say the intensity equals the sound. I equals the intensity of the sound. And then down here they say the intensity of the sound is this number. So we're going to take this and substitute it for I. And when we do, we get this. Because these are factors, you can cancel that out. So now we have 10 log 10 to the 12th. Whenever you have the base of the log equal to the base of the exponent in the argument, you can cancel them. And you're left with the exponent. So this becomes 10 times 12. Whenever we're multiplying, we know the number is going to get bigger. There's one 0 there, so we're going to make this number bigger by 1 decimal point, and it becomes 120. That's your final answer. Next one, number 20. Simplify each expression. So let's do that. Natural log of e to the 5x. So what do we notice? If you put the hidden exponent of the natural log, we have the base of the logarithm matching the base of the argument. That means we can cancel them out. And our final answer is 5x. Or, if that didn't jump out at you, we could set this equal to a variable and do whirlybird. So we can't pick x because it's up there in the exponent. So here we would do whirlybird. And we would try to solve for y. We would pattern match. Base is the same. There's an equal sign here. That means these have to equal one another. So y would equal 5x. But again, it's important to recognize this relationship. If the base of the log matches the base of the exponent in the argument, you cancel and you're left with the exponent. Next one is number 21. Here we go. Log to the base b of b. They ask us to evaluate it. Immediately, we recognize the base of the log matches the base of the exponent. There's an understood 1 there. Final answer is 1. If that does not jump out at you, we can do whirlybird. Put an x here. We can use x because it's not anywhere else in the equation. Remember, that's a hidden 1. We do whirlybird. We have b to the x equals b to the first power. We pattern match. X equals 1. Again, important to recognize this fact. At the risk of being repetitive, I apologize. When the base of the logarithm matches the base in the argument, these cancel and you're left with the exponent. Log to the base 6, argument 1. Set that equal to x and do whirlybird. There's only one thing x could be, and x has to equal 0. Next one, 23. Okay, now we're going to get into compound interest. So let's talk about compound interest a little bit. Compound interest formula is as follows. The amount equals the original amount times 1 plus the rate in a decimal form divided by n raised to the n times t. N equals the number of times per year that it's compounded. Now, the way I memorize this formula is that N stands for Nancy, and Nancy is very nosy. She likes to get involved. So she is listed twice. The rate is listed once, the time is listed once, but Nosy Nancy gets listed twice. Okay, now, if you see the words compounded annually, n equals 1, semi-annually, n equals 2, And monthly, n will equal 12. That's what you tend to see. Okay, let's look at this problem. 23. Suppose you have $3,000 to invest, so we're going to say that the original amount, P, is going to equal $3,000. Which investment yields the greater return over 10 years? So T is going to equal 10 for both of these. The first one, call that letter I. I'm going to move my board in a second. We have 6.5% compounded semi-annually. Okay, let's move the board up. Okay, whenever you see semi-annually, n is going to equal 2. We can't work with 6.5%. We have to change that to a decimal. The way I like to do this is instead of the percent sign, percent means per 100. Whenever you're dividing by 100, we know that the number is going to get smaller, and it's going to get smaller by 2 decimal places because 100 has 2 zeros. So I put some zeros into here. I know that number is going to get smaller because I'm dividing. Therefore, I move the decimal point twice. So 6.5% becomes 0.65, and that's what we're going to use for R in our equation. Okay, so let's go ahead and do that. The amount present is going to be 3,000, which is the initial, times 1 plus 0.065 divided by 2 raised to the 2 times 10. Again, the 10 is how many years, n is how many times per year that it is compounded. Because of Nosy Nancy, n is listed twice, and the amount that we get when you punch all that into a calculator is going to be 5,687.51. Okay, let's now move to part 2. And what do we see? Or 6% compounded continuously. Whenever you see these words, compounded continuously, E is going to be involved. Oops. Okay, so for part 2, %, compounded continuously. 6%, 6 divided by 100. There's the decimal point in its normal position. We're dividing by 100, so therefore we know we're going to get smaller. How much smaller? 2 decimal places. That's going to be your R. Now, whenever you have compounding continuously, you use this formula. P equals E to the R times T. Notice, Nosy Nancy's been kicked out of this equation, so she's gone. I'm sorry, that is not correct as written. I apologize. Sorry about that. A equals P to the ERT. Principal amount, this is A of T, and the constant E, the rate in a decimal form, and the time in years. For this problem, A of 10 is going to equal the principal, 3,000 e raised to the 0.06 times 10 years. Whenever we're multiplying, we know the number is going to get bigger. So we're going to go from 0.06 to a bigger number. How many times going to move the decimal place? Once, because there's only one 0 in 10. And you're going to get 0.6. When you do all the math, and you raise e to the 0.6 power and multiply by 3,000, you get this number. Therefore, part 1, where you compound it twice at the slightly higher rate of 6.5, is the better choice. Next one. How long, to the nearest tenth of the year, will it take 4,000 to grow to 8,000 at this 5% annual interest rate, compounded quarterly? Okay, so what equation are we going to use? Noisy Nancy's involved. Principal times 1 plus the rate divided by the number of times per year multiplied by NT. So we're going to have the principal is going to be 4,000. 1 plus 5% is 0.05. Compounded quarterly, that means 4 times per year, so N is going to equal 4. Time, we don't know. And A of t is going to be 8,000. So 8,000 is the amount at time t, which we don't know yet. So now our task, ladies and gentlemen, is to solve for this. Okay. First thing I would do here is divide both sides by 4,000. And we would now have two equals 1.0125 to the raised to the 4t. The way we would like to solve this is by using logarithms. So we're going to take the logarithm of both sides. We're going to take advantage of the property that lets us bring this exponent out front like so. That is going to give us log of 2 equals 4t times the log of 1.0125. We are then going to plug everything into a calculator and solve for t. Divide both sides by whatever this amount was. And when you do all that and all the smoke clears, you get t equals 13.94 years. Okay, that is the end of this sheet. Let's go to the next one. And do number 25. What interest rate, the nearest tenth of a percent, is required for an investment subject to continuous compounding to double in 10 years? Fascinating. Okay, so it says here it's going to double in 10 years. And they want to know, how long is that going to take? Continuous compounding. They don't give us any other information. They don't give us an initial amount. So continuous compounding, we know right away Nancy's not going to be involved. See if I can get this right this time. A of t is going to be the initial amount times e to the rt. Ladies and gentlemen, these three words provide for an incredible amount of information. Huge amount. It's packed with information. Because what does that mean? That means in 10 years, the initial amount is going to double. So when t equals 10, the initial amount, p, is going to go to 2p. That is a huge piece of information. Because look what happens. When you change a of t to 2p, you have p. We don't even have to know what it is. And we have e to the r times 10, because they tell us it's in 10 years. Look what happens. We go from all of these variables. Okay? Let's put a little asterisk to what we know. E is a constant, 2.71. The time, they tell us, 10. But we don't know what r is. We don't know what p is. And we don't know what a of t is. So in the beginning, we have one equation with three unknowns. It's an impossible task. But the fact that they tell us it doubles allows us to replace a of t with 2p. That is incredible, because then we can cancel out the p's. So not only did we lose a of t, we lost p in the process. So now all we have is that 2 equals e to the 10 times r. And now we are down to one equation, one unknown. We are in the catbird seat. We could solve for r. I'm sorry, I wrote that down wrong. What am I doing today? Yeah, 10. We could solve for r. Okay. And they want to know what interest rate. Okay, I'm sorry, I got a little confused there for a second. So we're trying to find r. We substitute t for 10. Now we're down to one equation, one unknown. And we could solve this. How do we do that? Okay, we have an exponent here that we're trying to solve. The variable's in the exponent. There's no way you can get a common base between 2 and e. E is 2.71. So in this scenario, you have to take logarithms to solve this. Now, which logarithm are you going to choose? Are you going to use regular log? Answer is no. You're going to use natural log. Whenever e is in the problem, you want to take the natural log of both sides. And the reason will become clear in a minute. It's because this is a base e, and whenever the base of the log matches the base in the argument, they cancel out. So now we are left with natural log of 2 equals 10r. So this we punch into a calculator, we divide by 10, and our final rate is going to be 0.0693. Whenever they ask for a rate, ladies and gentlemen, what interest rate, they want the answer in percent. And if you're not sure, put both down. Put the decimal and the percent form, so your teacher could see both. Okay. Let's quickly talk about how to make that into a percent. 0.0693 equals x percent. Whenever you see the percent sign, you replace that with division by 100. So now we have 0.0693 equals x over 100. Put a hidden 1 here. Whenever you have two fractions facing each other with an equal sign in between, It is an invitation to cross-multiply. Okay, so we're going to multiply 100 times this number. By definition, the number is going to get bigger because you're multiplying by 100. We're going to move the decimal point to make this number bigger. So the number is going to go from 0.0693. We're going to move it twice because there's 2 zeros in 100, and you have 6.93%. I understand, ladies and gentlemen, that many of you knew this right away. But if you do it and you're not sure, and you get on a test and you know they give you a funky number and you're not sure, just set this little equation up. And remember, whenever you see that percent sign, you divide by 100. Literally, in the word percent is per, that's always a fraction line. Cent means 100, just like century is 100 years. Next one. Okay, 26. So in 26 and in subsequent problems, we're looking at growth problems. Okay, so you have an amount. This is your principal amount, e raised to a rate. All right. The model for these equations are a of t, or I should say is, a sub 0, which is the initial, e to the k times t. Now, I did a separate video on growth and decay problems, which I welcome you to see, but we will be using this formula probably for the duration of this test. Here, in number 26, they give us the function right up front. And whenever they give you the problem right up front, they tend to be easier than when they ask you to find it. A problem like this usually just involves plugging in numbers. So let's do that. What was the population in Germany in 2010? Here the setup says that t is years after 2010. So in 2010, t would equal 0. I should write this function down. A of t So in part A, when you're in 2010, t is going to be 0. And if t is 0, then you have e to the 0, which is 1. So your answer is going to be 82.3. And that makes sense because that's the initial amount. Next one. Is the population increasing or decreasing? Well, whenever you see a negative there for the k value, that means it's decreasing. In which year will the population be 79.1 million? Okay, so we're asked to find t when a of t equals 71 million. So basically, a of 71 I'm sorry, that was wrong. A of t equals 71. So 71 is going to equal 82.3 negative 0.004 times t, and our goal is to solve for t. Okay, so in this scenario, what I would do first is divide by 82.3, both sides. When you do that, you get 0.961 equals e to the negative 0.004t. there's no way we could get a common base between these two to solve for t. So the only way to do this is logarithms. Which logarithm of both sides are we going to take? The natural log. Why natural log? Because e is involved. So when you take the natural log of 0.961, which is very calculator friendly, and the natural log, remember, there is a hidden base e here. Whenever the base of the log matches the base of the argument, you can cross them out and you are left with the exponent. So we are going to set natural log of 0.961 equal to negative 0.004 times t. Again, this is calculator friendly. You get this number, it's going to be negative. You divide by negative 0.004 and that gives you t, and the answer is 9.9 years. Again, problems like this, where you're given the model, you are often asked just to plug numbers in and find results. Now, here we go. In number 27, they want us to find the growth function. A little bit more difficult. Okay, so how do we do that, folks? All of these problems are the same. They all involve finding k. Once you find k, you can get the model. So what they're going to do is they're going to give you enough information here to find k, and you got your model. So let's see what they give us. If I go off the board, I'll come back. Okay. So in 2010, the population is 4121. I'm not going to write million because it's always millions. 2050, 5231. Don't forget, there's more information here, namely that t equals 40. All right, so here is a of t, here's a sub 0, and here's t. Okay, so we have a sub 0, a of t, and t. E's a constant. That'll let us find k. So let's do that. A of t, meaning a of 40, equals 5231. A sub 0, the initial amount, is 4121. We have e, we don't have k, and we have 40 as the time. We're going to divide both sides by 4121 first. When we do that, we're going to get 1.27 equals e to the 40k. Okay, I just swapped these two. We're going to have to take the log of both sides. You always look to see if there's a common base. There's no way you're going to get a common base. We're going to take the natural log, not the regular log. Why? Because e is involved. There's an understood e here. Whenever the base of the log matches the base of the argument, you can cancel them. We're left with the exponent. You have natural log of 1.27, very calculator friendly, equals 40k. You punch this in, you divide by 40, and you get your k. And k is going to equal 0.006. And always ask yourself, does the k make sense? If k is positive, which it is here, it's a growth problem. And indeed, here's a growth problem because between year 2010 and 2050, the population grows. Next. Okay. First half-life problem. Okay. Use the exponential decay model. This is also the exponential growth model. What makes it a decay or growth is whether or not that K is positive or negative. So let's write down the formula. A of t. I like to put A of t because it reminds you that it's the amount after a certain amount of time. Okay. They tell you the half-life of iodine is 7.2 days. Okay. Now, how long will it take for a sample to decay to 30% of its original amount? All right. The whole key to these problems is to get the model. And the model equation always comes down to finding K. They're going to give you enough information at the outset to find K. All right, let me just write down the particulars here so I don't have to keep moving my screen. How long will it take to get 30% of the original amount? So T equals question when 30% of original is present. Okay. The goal here, ladies and gentlemen, is the same in all of these problems. We're going to find the model, which involves finding K, and then we can handle any question they ask us. If they want to know the time of 30% of the original, we can do that. If they want to know the time of 50% of the original, anything they throw at us, we can handle it. Now, it's important to recognize the power and the value of this one innocent-looking statement. Half-life is 7.2. Just like a few problems back, we talked about the doubling time. I can't remember what the other problem we did earlier in this video, but it had to do with doubling. And I told you how important that was and how that led to us being able to eliminate variables and go down to one equation, one unknown. The same thing is true here. Half-life equals 7.2 is a huge amount of information. Because what does it tell us? It tells us that when t equals 7.2, A of t is going to equal 1/2 the original amount. That is a huge help to us finding the equation. So now, instead of A of t being an unknown, we know that they're looking for 1/2 of the original amount. Again, we don't know K yet, but they tell us T. These A sub zeros drop out because we divide both sides by A sub 0. We now have the incredible advantage of having one variable, one equation. Now, once we solve this, we're going to go back, create our model equation, and we're going to be able to handle anything they throw at us. So let's do that. Let's find K here. I appreciate your patience, folks. Okay. We're going to make that 1/2 calculator friendly and do this. 0.5 equals E 7.2K. We need logs to solve this. We're going to take natural log, not regular log, because we have E. We're going to take advantage of the fact that this cancels. We're going to be left with this. We're going to get the ln of 0.5, calculator friendly, equals 7.2K. Punch that in, divide by 7.2, and we get, K equals negative 0.0963. Now, does that make sense that K is negative? Definitely. This is a decay problem. Okay. So now we plug the k back into the generic equation. So we take out all of this. Once we have k, we have the model. So here's your model. This problem is now over. We can handle any question they throw at us. Okay? They want to know what's the time when you have 30% of the original. No problem. A of t equals 30% of a sub 0. 30% of a sub 0 equals a sub 0 e to the negative 0.0963 t. Those a sub zeros beautifully cancel out. Now we have 0.30 equals e to the negative 0.0963 t. We take the natural log of both sides. Natural log 0.30 equals natural log of e to the negative 0.0963 t. These cancel out. You get natural log of 0.30 equals this. You use your calculator, and your final answer is going to be 12.5 days. Again, I encourage you to do that with your calculator, just so you get facile with it. Okay, folks, we're almost done, because we're going to skip all the way down to the last problem, 34. Okay, so this is a tricky problem. So I'm going to write it down, and we're going to talk about it. And the beauty of videos is that you can just keep rewinding and come back to it. You could stop in the middle, come back at another time. That's what I love about working with videos. Okay, so they want us to rewrite this in terms of the base e. Okay, in terms of base e. Okay, let's talk about what they want. This equation is currently in the form of y equals a times b to the x. Now a throughout this discussion is going to stay the same. The action has nothing to do with this 96. That's going to be carried down all the way down, and we're not going to mess with that. But this is fascinating. So in this particular problem, b is equal to 0.38. Let's talk about what b is also equal to when you have e involved. Okay, so here's a generic statement. If you have the natural log of e if you have e raised to the natural log of e to the base b, that equals b. Whenever you have an exponent, whenever you have an exponent raised to a log with the same base, these cancel out. It's the same thing as when we have this. Here, on the right, you have a log with the base the same as the exponent. They cancel and you're left with the base. On the left, you have an exponent with the same base in the log above it, and those cancel out. So we're going to use that trick here. So if b equals 0.38, okay, all we're going to do is plug in 0.38 instead of B. So we're going to say e to the natural log base e of 0.38. So instead of the base equal to 38, instead of the base being 0.38, we're going to take this and we're going to move it and put that in for here, right there, because they are the same. This red statement, or actually I'll circle it in yellow. This yellow statement right there reduces to 0.38. So all we're doing is plugging what's in yellow in for 38. Totally legal. So our final answer is going to be, sorry, this is really messy. Like I told you, the 96 we didn't even discuss. E to the ln of E 0.38 times x. So that's how you do that. And the reveal here is that this cancels out. So that is the same thing as just 0.38 to the x.